everyone. My name is Mantas, and I'm an engineering manager for one of the observability teams in Danske Bank. And my main focus is integrating all of the different platforms that we have in Danske Bank to our central observability stack. And this is Marius, my colleague, who is the area architect, focusing mostly on data quality, correlation, and data presentation for all of the signals that we support. So in Danske Bank, we have around 60 different platforms and 90 components. Each of those components might be a Linux machine or a Windows machine, and those platforms could be an operating system. So the platforms consist of the components. All of those platforms are there to support over 1,000 applications. Each of them might have dozens or hundreds of different deployments, different microservices, and they might rely on dozens of different platforms. To really crank the complexity dial up, we are now migrating to AWS, which is another 50 platforms right there, and growing constantly. We are really trying to integrate as many platforms as we can, because if there's a fire in some place in the city, it would be good to have an illuminated road to that fire and not have any pitch black spots where you might miss something. So where do we start? We start with collecting the data from the producers, the applications, the platforms that we have. Ideally, they can not only produce those signals that we are interested in, but also send them to us. Send them to our ingest pipelines, where we just set up listeners and we receive the data and we act on it. But it's not as easy as it seems, because as you can imagine, not all platforms are built the same. So some of them are easy to integrate with modern observability tooling, and some not so much. So for those, we need to build collection systems or tools, a collection layer that we call. Those are there to really connect to a specific platform and get a specific signal from it, export it to our supported format, and send it to our ingest. We have plenty of those collectors. For example, we know that in AWS, lots of AWS services support S3 for logging, so we integrate with S3 to grab those logs. We integrate with CloudWatch to grab those metrics. We integrate with CloudWatch to grab logs as well. We have collectors deployed on all of the operating system machines in the bank, both on-prem and in the AWS EC2, both Windows and Linux. That totals around 16,000 agents deployed across the estate to read the logs from the machines, to read the metrics from all of the exporters within those machines. So it might not just be a node exporter collecting operating system metrics. It might also be MongoDB. It might be web server. It might be Microsoft SQL on Windows. And we grab all of those metrics, we transform them to a supported format, and we send them to our ingest. There we need to really make sure what we're doing, because, for example, a thing like MongoDB could be running on Linux, but it could also be running on OpenShift. And we need to handle those cases so that at the end of the day, it should be presented in a single Grafana dashboard without the need to specify which platform it is running on. Another collector that we have is running on OpenShift. So those are agents deployed on all of the OpenShift clusters in the bank, collecting logs from all of the pods that are generating std out logs. Those logs get sent to us, and here we also need to pay extra attention, because not all logs are interesting for everyone. Some logs coming from OpenShift are only interesting to the OpenShift administrators, to the platform owners. Others are only interesting for the application owners that are running on those OpenShift clusters. So we need to handle them differently. We need to separate them out. We need to put them into different buckets on our storage of choice. And we need to expose them to different users. So we collect all of this data using collectors or directly. We ingest it, we store it in our backend of choice, our storage of choice. We present it in Grafana, give it to users, and we're done, right? Well, there's a little bit more to it than that, because when giving this mix of data, this huge pool of data to users, it is really, really difficult to make sense of it. Especially if you're not an expert in all 150 components that we have, and no one is. So how do we, especially considering the amount of data that we have. So for logs, we have close to 2 petabytes of data ingested every year. For metrics, we have around 300 million active series right now. So that could be a topic on its own. I'm sure our friends at Vinted will talk about it more today. We can maybe learn something. So what can we do to help out the users to get the sense of this data? Well, we can do some work on the ingest layer. We can remove some of the complexity by changing the field names, by unifying some of the data. So if we receive an environment name that is in different casing in different platforms, we can try to unify it to have the same casing so that the user can search for it and find the right information. We can do a little bit of more of merging of data like this. So if there's 5 different network platforms that call the same thing, source IP, in different ways, one platform might call it SIP, another source-IP or whatever else, we can rename all of those to match a single type of field. But that's still not enough. And we were thinking, what can we do in addition to this? And what we really needed was a common interface, a common structure for all of those signals, so that users can interact with this common interface and without knowing the intricacies of every single signal that is behind, whether it's logs, traces, metrics, or anything else. So this common interface we call Danske Bank common schema that we apply for all signals. But unfortunately, it cannot fulfill the promise because we cannot get the data that we have into that schema in quite a few cases. We simply don't have enough information in the originating message to comply with that schema. So we need to add additional information. For example, if we get the same log message that says source IP X tried to connect to destination IP Y, we don't know what those IP addresses are, and we have no way of knowing because the source system doesn't know. So to answer this problem, we have MDB, which is kind of CMDB, a live view into our whole estate, which has information about all of the platforms, all of the platform groups or components, all of the instances of those components, and the relationships between them. So having this power, this data in our tool set, we can achieve quite a few things. If you have a live view into all of your infrastructure across all of the platforms, you can do discovery for your collectors. If we have a Prometheus instance scraping the different load balancers out there, and if there's a new load balancer being provisioned by a network team, by our colleagues, and we don't want to be informed about that, we want to automatically update the configuration. So we look up the latest information about all of those load balancers in MDB. We update the scraping targets dynamically along with all of the information necessary to configure it. The second thing that we can do is enrichment. So this is finally something that we can use to reach our common schema. So getting back to that IP address that we received that we don't know anything about, we can look it up in MDB. Once we look it up, we add context to this message, context that the originating platform didn't have and that we didn't have. So we add an additional field called source environment, which is prod. We can add source data center, source availability zone, source owner. So we can enrich the data and we can really fill in the gaps to comply with our ideal schema. We also use MDB for variables and correlation in Grafana, so that you can always be sure that all of the application names are populated correctly because they are discovered automatically. And finally, there's another use case that we have that I haven't mentioned yet, and it's about alerts, which is an often overlooked signal. We treat it as a signal, even though we have Grafana as our tool of choice for alerting. We cannot ignore the fact that we have 20, 30, maybe more other alerting tools in the bank that are producing signals that can only be described as alerts. We have worked hard with those system owners to integrate those systems with us, with our stack. So we receive all of those alerts from Grafana, including our instance, other instances in the bank, from alert managers, from mainframe services, from devices generating us NMP traps, Isinga instances, even Sensu. We have all of those alerts reaching us. And we, utilizing MDB and all of quite a few different strategies, we enrich those alerts, we unify them into a single view, into a unified alert, which is also matching our schema, and we send it off to AMS, which is an internally built alert management service, specifically designed to handle those. Those alerts can be viewed in Grafana or in a UI that has a self-service component where you can set up incident flows, automation flows, automatic callouts, and so on. So how do we ensure that we have the right data in the MDB, as it must be up to date? Well, we follow the same approach as for other signals. We set up collectors for all of the systems, for all of the platforms that we need. We have one for AWS, for Cloud 2, which is our internal cloud platform. We have for DNS, for Chef, for ServiceNow, and so on. We extract raw data about the components, the instances of components, the properties, all of those things. We send out the raw data into our ingest pipelines, and we really craft the objects that we want to get out of it. So if we want to have a list of all Linux machines, how do we achieve that? There's no golden source which has all of the information that we need. So we take a little bit from Cloud 2, we take a little bit from DNS systems, we take a little bit from Chef, we take from ServiceNow to maybe look up ownership information. And we craft a single document that describes a Linux instance. This instance, this object, can have relationships to other objects, to other Linux machines, to the physical hosts, to the network devices, to the IP addresses, and so on. It can have also relationships where we attach signals to this object, so that we know that if an alert was generated, it was generated on specifically this object, and we can uniquely identify them. How does this document look like? Might be a bit of a simplified view, but we have mandatory fields to describe each object, whether it is a resource, a signal, an alert, whatever. We have categorization data, where we categorize it to some user-friendly categories. We have ownership and environment information to identify unique applications, or SPIs as they are called in Danske Bank. We have location data, both physical and network. We have segmentation, and we have resource identifiers, one of them being a unique identifier of every single resource that we have that can, on its own, provide quite a lot of value. So we have the schema, we have the signals. We're still not done, because we still have quite a few components to cover. We have 150 or so components that we need to apply this to. So if we take one of them, a Linux server, we need to ensure that we have those machines discovered. We need to ensure that logs, metrics, and traces, if they are applicable, are collected. All of them comply with our schema, so modifications are done, enrichment is done. Once that is done, and the schema is in place, we need to set up KPI metrics for each of the machines, for each of the Linux servers. We need to set up anomaly detection. We need to set up sampling for traces, and we need to set up metric generation from traces. In addition to that, we want to set up alerts so that users can, without knowing the intricacies of this specific component, a Linux machine, a load balancer, whatever it is, they can take alerts off the shelf, pre-made by either platform owners or us in the observability area, and they can set up alerts. They can subscribe to those alerts if they are interested for the components that they rely on. And finally, we want to have visualization to visualize everything that we created. And here I will pass the mic to Marius.
To show visualization.
To show visualization.
This is the main page of Grafana. Okay, so as Mantas mentioned, we are discovering a lot of systems, and you can see it here. Everything is in the main, so you can see how many components, how many assets we are discovering per each platform. So let's say there are 150,000 pods, and there are a bunch of load balancers we use a lot. In this case, it's Netscaler. We're using OpenShift. There are runtimes, SQL servers, a lot of services. So around 80 services right now is onboarded, and we can, in a single view, look into all the signals which is produced by these components. So right now we are looking on 300,000 of components, and we know how many of these components incidents is created, how many alerts is created, how many change is done on these components, how many events happening, and how many logs it's generated. We a lot doing schema for every signals, and this is very important for us. I'm gonna show you a little bit first dashboards which we use for exploring. So each signal, we mainly have the explore dashboard, where if the signal fit the schema, the dashboard gonna work out of a box. So let's say if we have the MDB data, I can show some examples how actually MDB data looks behind the scenes. So it is just a JSON file stored in Elasticsearch. It sounds pretty simple, and you can pretty easily query this data, and you can see how many different attributes we are collecting for each of the object, and we have many of those objects created. So you can use the MDB data for many reasons. You can find who using image, how many VMs running in one data center or another. So it is very easy to query, because you can use just Lucina query language, which you're using in Akibana, to find and match text search any attribute inside the MDB document. When we do the same with alerts, with events, let's say, so we're using the schema, ECS schema, it is Elastic Common schema. So we would like to always see events in the same form, to be able to read it in a single dashboard. So if events is in a schema, so you automatically can get all events in all your infrastructure components. So right now I'm showing OpenShift events which is happening in our platforms. We do the same for web logs, network logs, so we can use the single dashboard for browsing all the web logs together. In this example, there are, let's say, 3 platforms here. You can see there are missing SPIs. So in all dashboards, we're using the same variables. So the users they're going, selecting their SPI code as application name, and they should get all the data collected from that specific SPI code. Here is missing SPI because initially logs from AWS, they doesn't know anything about the SPI code or something like this. So what we're gonna do next, we're gonna discover these components, read the tags, get into MDB, and then merge logs and MDB data together, and then as a result we're gonna populate the SPI codes as well. So the next users gonna be able to find their SPI codes on their the logs. So it's a lot of things. It is in progress, what we need also to do, but a lot of things already is also done. For metrics, so we're creating key performance metrics. It's just like aggregation of the metrics. We're using Prometheus ruler, create some metric aggregation. Then user doesn't even need to know much about PromQL and create a complex query of how the CPU usage looks like. They out of the box have a bunch of pre-created queries which they can use in their dashboards as well without even knowing a lot about the PromQL. This is one thing. Another thing, what you can look into the different components very quickly. Let's say I now looking into the single SPI all Linux machines, and I see all performance metrics of these all machines. And this is grouped by microsegment. I can group, let's say, by enclave or SPI code. If you have, sometimes our application have 2,000 components, 400 virtual machines, and you need to understand how they perform in different data centers, so you need to group somehow this data. And here, let's say I can choose another platform, let's say AVI, and I instantly could get all the key performance metrics of AVI. If I choose, OpenShift, I get OpenShift Ingress key performance metrics. This is useful when you have a, big infrastructure. Next, what we also do, we do anomalies. Sometimes it's not enough to have static threshold for your alerts. You need to have some dynamic patterns to be detected. We're using pretty simple Grafana Prometheus-based framework, which is actually based purely on the Prometheus ruler, where you can just adding some tags on the metric, and you can get as an output the new metric which generates some upper lower bands which you can use later for alerting. Okay, so it's very useful as well. Then for each platform, let's say you have Linux machines here, there are 100 alerts. I wish it's not in production. So each platform, when we're onboarding, we're creating some kind of global alerts. And you can see how many alerts which we are setting up on all the machines. And it's happening, and alerts happening sometimes, and you can use it for correlation. It's not mean that you will wake up at night by each of these alerts, but you can subscribe these alerts, create an incident from this alert, and say what I would like to do some actions if this alert is happening. But you still, when you're running machines out of the box, what there are a bunch of known things which might break your system is covered. Why this labeling important as well? Because when you storing the alerts, you can grab these labels and then try to slice and dice data by different fields. Let's say I can look for platforms, so and we had spike of alerts in OpenShift. So it's important what you can see alerts in a time range, not like, okay, this is alert happening here or here. You need to understand how to these alerts, changes, incidents is correlated in the time. So this is also well work for us as well. Now I don't have probably much time. I show you another dashboard. So because you heard MDB is just Elasticsearch which stored JSON document. So basically I can ask to query anything, So let's say I have IP address. So I can query IP address and find the component which have this IP address. It shouldn't be a big deal. So now I see, okay, this is AVI virtual IP, this is resource name, this is how many request errors duration is happening, and this is alert which is firing right now. So if this component have performance metrics, I can instantly use it. So I can write a query saying, give me the whole application, give me all DC1 machines, Linux machines, and I can do anything I like if I know. Even I don't need to know the field name because it is Elasticsearch. You can just text query. Then you have this all, the signals which you can read, but more on that, you can have some kind of topology. Now, this is a single component, so I know about this single component everything that I need, but if I, do downstream dependencies I get the all components which is connected to this. And now, instead of I see that there are errors happening on VIP, I can see that there are pool which points to Windows Server which have IIS running on it, and IIS also have an error. So this is how we can correlate. So you can imagine you can use GenAI. You have very important incident, very important alert happening. You can write agents which would do for you, grab the topology, grab all the alerts which happening in the time range, and then say, okay, the possible root cause is this is events which is happening at that time, this is logs, this is key performance metrics. This is, you see, the connections. We have zero trust, so everything going through firewalls. We're grabbing all firewall logs and then aggregating and saying, okay, I know from firewall that this server A talks with server B, they are related. We don't need to do even tracing. We can get this relation straight from the firewall logs, from the traces, from the configuration, from any other data sources, which it's allow us to make this happening. That's it. So the future is bright. A lot of things we need to onboard. A lot of AWS platforms is in queue, and GenAI maybe next time. Thank you.